All right, this is our circuits test review. Let's jump in. The potential difference, that's the voltage across the ends of a wire, is doubled in magnitude. If Ohm's law is obeyed, which of the following statements concerning the resistance of the wire is true? Well, it turns out the resistance is not changed. Resistance only depends on what the resistor is made of, the resistivity times the length divided by the area. If Ohm's law is obeyed, resistance doesn't depend on current or voltage. It's independent of those things if Ohm's law is obeyed. Complete the following statement. The unit kilowatt-hour measures. Now, we haven't dealt with kilowatts and we rarely deal with hours. So what I want to do, instead of thinking specifically about what those units are, is to think about what type of thing they define. So, a kilowatt is power, an hour is time. Power times time is energy. Kilowatt hours are how the power company measures how much energy you use. But power times time gives you energy. Sometimes it's easier to think in broad things than it is the specific units. All right, a 40-watt bulb and a 60-watt bulb are designed for use with the same voltage. What's the ratio of the resistance of the 60-watt to the resistance? Well, all right. What we have to get is from power, we're going to get resistance. So, power is equal to current times voltage. That doesn't have resistance in it. I also know that current is equal to voltage over resistance. So I'm going to put that in there. That gives me power is equal to V squared over R. So here's the deal. We have the power. We know the voltage is the same. We don't have the resistance, and we want to compare those two things. So what we're going to do is solve for V. V squared equals R times power. And we're going to set them equal to each other, right? So V squared equals R1 times power 1, and V squared is equal to R2 times power 2. So I'm going to say R2 power 2 equals R1 power 1. And then just to kind of give us the things that we're talking about, R of the 40 watt times 40 watts is equal to R of the 60 watt times 60 watts. And we want 60 over 40 because 60 comes first. So R60 over R40 equals 40 over 60. So it's 2/3, 0.67. There's a lot of work for that. Important parts of that question, just as things to hold on to, are how we get different things for power. Okay, so we have one equation for power. That's all you're going to get, P equals IV. What we're going to do is substitute some version of Ohm's law in there based on what we have. So we can have P equals V squared over R. We can have P equals I squared R. Depending on what we plug in. So those three things are the real three equations for power, depending on what we want to do with that and what we have. And it'd be nice to be able to know how to get to those two things by inserting Ohm's law. So, a 5 amp current is maintained in a simple circuit that consists of a resistor between the terminals of an ideal battery. The battery supplies energy at a rate of 20 watts. How large is the resistance? We have 5 amps, 20 watts, and we want to know the resistance. So we're going to use this equation for power. Power is I squared R. So R is equal to power over I squared. So that's 20 over 25. 20 over 25 is 0.8. Which of the following statements concerning resistors in series is true? Well, when we're in series, the current is the same all the way through, and the voltage is add. So the voltage across each resistor does not have to be the same. It depends on the resistance of each resistor. But the current through each resistor has got to be the same. Three resistors are connected in series. So if we continue this idea up here, where we've added the voltages together, and we know that voltage is IR, then we have I total, R total equals I1 R1 plus I2 R2, possibly plus I3 R3. And since all those currents are the same, we can cross them out. And R total is just R1 plus R2 plus R3. In series, resistors add. So 50 plus 100 plus 200 gives us 350 ohms. Number 7, a 4.5 volt battery is connected to two resistors in series as shown in the drawing. Determine the total power dissipated by the resistors. So, that's a complicated-ish circuit. What we can do is make it less complicated by adding our two resistors together. Now, 1, it says there in series. 2, if we follow this circuit, I have to go through both resistors. If you have to go through both of them, that means they're in series, which means we add them together to get their equivalent resistance. So 68 plus 68 is 136. There we go. So we have 136 ohms, 4.5 volts. I know that power is current times voltage, but I don't have current, so I know current is voltage over resistance. So power is voltage squared over resistance. So 4.5 squared divided by 136. Power is 0.1489 watts. So we'll say just 0.15. Number 8, some bulbs are connected in parallel to a 120 volt source as shown in the figure. Each bulb has a power of 60 watts. The circuit has a fuse F that burns out if we get more than 9 amps. Determine the largest number of bulbs which can be used without burning out the fuse. Okay, so an illustration is going to help here. We have 120 volts. We're going to put in one of these resistors. We're going to put in one of those. We have a little fuse. Talk about a fuse. Okay, so I have 120 volts and 60 watts. Power is IV. So through that one light bulb, the current is power over voltage. So that's 60 watts over 120 volts or 0.5 amps. So in this resistor, we have 0.5 amps coming through. Boom. So one resistor, one blue line is 0.5 amps. So let's say we add one more resistor. That resistor has been added in parallel. That doesn't change the current through the first resistor, but what it means is that I get an additional 0.5 amps of current coming from the battery. So now I have 1 amp of current coming from the fuse, going through the fuse. Each additional resistor that I add is going to put 0.5 more amps through the fuse. So if I can go up to 9 amps before we break, that means we're going to have one less than that, or 17 bulbs. When I have 17 bulbs, I didn't draw 17, but when I have 17 bulbs, I have 8.5 amps running through there. I get to 18, that's 9 amps, and we'll break. So in parallel, total current is current through one branch plus current through the other, on and on and on. And through this fuse, we're getting the total current. So every time we add another branch, all we're doing is increasing the total current. Three resistors are connected in parallel in a circuit. What's the equivalent resistance of this combination? So to just get us on the right foot with parallel, the voltage is the same all the way through in parallel, and the current is what adds, like we saw above. So if the current is what adds, and current is equal to voltage times voltage divided by resistance from Ohm's law, then voltage over current total is voltage over current. Then voltage over resistance total is equal to voltage over resistor 1 plus voltage over resistor 2 plus voltage over resistor 3. All the voltages go away, and 1 over resistance total is 1 over resistor 1 plus 1 over resistor 2 plus 1 over resistor 3. So 1 over the total resistance, we're just going to add like that, is 1 over 6 plus 1 over 9 plus 1 over 15. If you put all of that into your calculator, you get 0.344. So 1 over R total is equal to 0.344. I'm not looking for 1 over R total, I'm looking for R total. So that's 1 divided by 0.344. If you're going to make a mistake with things, this is one of the mistakes that you could possibly make. You must take the inverse. Before going through with this. So that gives me a total resistance of 2.9-ish ohms. Use the following to answer questions 9, 10 through 12. Three resistors are connected as shown. The potential difference between these points is 26 volts. So if we could redraw this and give ourselves point A, 3 ohms, 2 ohms, point B, but the 2 ohms is in parallel with 4 ohms. That would be connected to a 26 volt battery. That's another way of, well, let's make sure it's connected. That's another way of looking at this circuit. So what we want to do is simplify that top part so that we can figure out what's going on here. So 3 ohms. And then we have a combination here of the 2 ohms and the 4 ohms together. So 1 over 2 plus 1 over 4 is equal to 1 over R. So 1 over R is equal to 0.75, making R equal to 1.33 ohms. And all that's connected to a 26 volt battery. So we can put all that together, and overall we have 4.33 ohms connected to a 26 volt battery. So what's the equivalent resistance between points A and B? 4.3 ohms. How much current flows through the 3 ohm resistor? Now we get to do some work. So here the total current, and I can only do total current, and I can only do total voltage, I can only do total resistance at one place, and that's where we're looking at everything. So 26 volts divided by 4.3 ohms. That total current comes out to be just about 6 amps. That means I have 6 amps running through that total resistance. But that total resistance is a combination of something in series. And in series, I know that the total current is equal to the current through each resistor. So the 3 ohm resistor and the 1.33 ohm resistor each have 6 amps running through it. So if I want to know what's going through the 3 ohm resistor, it's 6 amps because it has to be the same as the total current. How much current flows through the 2 ohm resistor? Okay, now we have to continue going with the things that we know here. So looking at that, 6 amps, 1.33 ohms, what I can get is the voltage. Voltage is current times resistance. Now since I'm talking about an individual resistor, I have to take the current through that individual resistor, 6 amps, times the individual resistance, 1.33 ohms. That makes the voltage here 9 volts. Now, that stuff that's circled is a parallel combination. In parallel, it's not the current that's the same, it's the voltage that's the same. So, with the 2 ohm resistor and the 4 ohm resistor, we're dropping 9 volts over each. So if I want to know what's going on with the 2 ohm resistor, the current is going to be the voltage dropped across that resistor divided by the resistance of that resistor. So 9 volts, not all 26, divided by 2 ohms is, did I do something wrong? Sorry, 1.33 times 6 is not 9, it's 8. Math is hard. So that's 8 volts. 8 volts divided by 2 ohms is 4 amps. Alright. 4 resistors and a 6-volt battery are arranged as shown in the circuit diagram. Determine the equivalent resistance in this circuit. So we got 6 volts. We're going to leave the 20 ohm thing alone for now. It's not the most complicated part. In fact, we're going to leave the 10 ohm for now, and we're going to attack this parallel combination. Well, this parallel combination of 30 and 60, 1 over 30 plus 1 over 60, and 1 over my resistance, that gives me a total resistance of 20 ohms. So now we're going to combine those two, 6 volts, 20 ohms. We combine that branch and we get 30 ohms. We put it together in parallel, so 1 over 20 plus 1 over 30 is 1 over R. And that makes the total resistance 12 ohms. So we got 12 ohms here. So the equivalent resistance in this circuit is 12 ohms. The smallest current passes through which resistor? So, let's pretend we're the current coming out of the battery. We come out of the battery, we get here, and we split. Okay, so then that stays the same. So there's no more splitting for the 20 ohm resistor. Then our current comes through here, and it splits at this junction. So that tells me that the 30 ohm and the 60 ohm have a current that has been split or reduced. Well, not reduced. We have current that has been split twice. Now, at this split for the 30 and 60 ohm, which branch has more current? Well, if we look at that, current is voltage divided by resistance. Well, those two things are in parallel, so they're going to have the same voltage. So we're going to have the smallest current through the thing with the greatest resistance. That means the 60 ohm resistor has the smallest current through it. Very good. The largest potential difference is across which resistor? Okay. So, across the 20 ohm resistor, I have all 6 volts. Right? So here I've got to have 6 volts, here I've got to have 6 volts, here I've got to have 6 volts. All along that top wire, there's nothing to make the voltage go away. And anything connected to the back end of the battery has to have 0 volts. And I'll spot right there, 0 volts. So, from here to here, we drop all 20 volts. We drop all 6 volts. So there are 6 volts dropped across the 20 ohm resistor. I lose some, that's less than 6 volts, across the 10, and then an equal amount across the 30 and the 60. So, looking at it, the most potential difference is across the 20 ohm resistor. All right, numbers 16 through 19, it's similar to one that we've already done. So again, what we need to imagine is that between points A and B, we have a 30 volt battery. But before we can do anything with that, we need to combine the 30 and the 60 into one resistor. So 1 over 60 plus 1 over 30 is 1 over R. Solve for that. Take the inverse. R is 20 ohms. Not 2 ohms. 20 ohms. And again, that's connected to a 30-volt battery. Reduce that down to something that is 30 ohms connected to a 30-volt battery. So at that circuit, looking at it, the current is 1 amp going through that 30 ohm resistor. That means the current through each of these is 1 amp. And since voltage is equal to current times resistance, we have 20 volts dropped on this resistor, 20 volts dropped on this resistor. And because this is a combination of things in parallel have the same voltage dropped across them as the total resistor. So that's kind of the whole circuit. Oh, and then to get the current through there, it's 20 volts divided by 60 ohms. It's 0.33 amps, and then 20 volts divided by 30 ohms, 0.66 amps. You add those together and they go back to 1 amp. So the equivalent resistance between points A and B, that's the total resistance there, is 30 ohms. The potential drop across the 10 ohm resistor, that's just that right there, 10 volts. Potential drop across the 30 ohm resistor, since it's part of that parallel combination, it's going to be 20 volts. And the current through the 30 ohm resistor, since it has a 20 volt drop, 20 volts divided by 30 ohms is 0.67 amps. Similar problem, determine the current in one of the 16 ohm resistors. So we have to take and combine those 16 ohm resistors into one resistor. So 1 over 16 plus 1 over 16 is 1 over R. Solve for that and take the inverse, and R comes out to be 8 ohms. (24 volts). So combine those down again, and my total resistance in this circuit is 16 ohms. So I have 16 ohms and 24 volts. The current is 24 volts over 16 ohms. That's 1.5 amps. So in this circuit, we have 1.5 amps running through all 16 ohms. But since that's a combination of things in series, and in series, current is equal to current is equal to current, the same total current is the same as the individual currents. Each one of these has 1.5 amps running through it. Now we know the resistance of each resistor and the current running through each resistor. So the voltage is going to be the current through that resistor times that resistor. So the voltage for this 8 ohm resistor is 1.5 amps times 8 ohms, or 12 volts. And then 1.5 amps times 8 ohms, or 12 volts. Which makes sense because in series, total voltage is voltage 1 plus voltage 2. So these two things should add up to the total of 24 volts. But moving back to here, that is a combination of things in parallel. In parallel, the total voltage is equal to the individual voltages. So if I've got 12 volts on each resistor, 12 volts total for that combination, then each resistor has 12 volts dropped across it. And so in order to get the current would be the voltage across that resistor, 12 volts, divided by the resistance, 16 ohms, which is 0.75 amps. 0.75 amps. 21, to get the total power dissipated by the 40 ohm resistor, power is IV. I don't know any of that for the 40 ohm resistor. Power is V squared over R. Well, I don't know the voltage, and power is I squared R, and I don't know the current through that resistor. So we're going to have to do some tricky things to solve it. So we have a 4 ohm resistor. We're going to combine these two things that are in parallel. 1 over 40 plus 1 over 10 is equal to, I believe, 1 over my resistance. So 1 over the resistance is 0.125, making that resistance equal to 8 ohms between those two. So combining it down, you get 12 ohms and 18 volts. So if I want the total current, it's it's 18 volts divided by 12 ohms. And that's 1.5 amps. So I have 1.5 amps running through there. Since that's a combination of things in series, total current is equal to the individual currents. So I have 1.5 amps through that, 1.5 amps through that. Because we know that, I don't need this anymore. Because we know that voltage is equal to IR, I can get the voltage across this 8 ohm resistor. 1.5 amps times 8 ohms gives me, it looks like an R, gives me 12 volts. 1.5 amps times 4 ohms gives me 6 volts, which makes sense because those things should add up to 18 volts. And that's just a combination of things in parallel. Well, in parallel, voltage is equal to the individual voltages. So I have 12 volts here, and I have 12 volts here. So if I want power, let's go with this one. It's going to be the voltage 12 squared divided by the resistance of 40. So I get 3.6 watts for the 40 ohm resistor. If you instead solve for the 4 ohm resistor, you get 9 watts. It's kind of tricky with the periods there. All right. For this one, what's the equivalent resistance of the circuit? So we're going to go through and we're going to combine things. The first thing we combine is the 10 ohm resistor. So I have 100 volts, 5 ohms. And we put those two 10 ohm resistors together. 1 over 10 plus 1 over 10 is equal to 1 over R. You get 0.2. So R comes out to be 5 ohms. And then looking at the equivalent resistance, we get 10 ohms. So the equivalent resistance of this circuit is 10 ohms. The current through the 5 ohm resistor, well, to get that, we need to see what's going on. One thing we cannot do, ever, no matter what, is say that the current through the 5 ohm resistor is 100 volts divided by 5 ohms. The reason we can't do that is because that is total voltage, and this is an individual resistor. I cannot do that. The only thing I can divide total voltage by is total resistance. So this is not allowed. You cannot take the voltage of the battery and divide it by just one resistor. You would be doing it wrong. You will miss the question. Do not do that. In order to do it, you have to combine your circuit like this and work backwards with the things that you know. So the first thing that we can find out here for my total circuit is that the total current in the circuit is equal to the total voltage divided by the total resistance. Notice that it's total voltage divided by total resistance. So that's 100 volts divided by 10 ohms. Total current in my circuit is 1 amp. So I have 1 amp moving through that 10 ohm resistor. That's a combination of things in series. And in series, the total current is equal to current 1 is equal to current 2. So that means I have, not 1 amp, 10 amps. It means I have 10 amps through that, 10 amps through that, 10 amps through each one of my 5 ohm resistors. In order to figure out the rest of what's going on in this circuit, voltage is current times resistance, so 5 ohms times 10 amps gives me 50 volts for each one of those. That means that I completely have this 5 ohm resistor figured out. It's 50 volts and it's 10 amps. And all of those things work together. For that resistor, the current is the voltage through that resistor divided by that resistance. 50 volts divided by 5 ohms gives me 10 amps. That I can do. So the current through that 5 ohm resistor is 10 amps. What is the voltage dropped across one of the 10 ohm resistors? Well, those are a combination of something in parallel. And in parallel, the total voltage is equal to each one of the individual voltages. They're all equal across the board. So if I have 50 volts here, I have 50 volts dropped across each one of those. So, number 4. Let's say the 5 ohm resistor burns out, it fails, we have a disconnect, a break in my circuit. If that's the case, I do not have any complete loops that current could flow through. So there's no current. So the current in each one of those resistors would be 0. I have no complete circuits there. Now let's say this fails and I have no current going through here. So my current can only travel on this path. So if one of those 10 ohm resistors fails, instead of having 5 ohms and 5 ohms total, it's 5 ohms here and 10 ohms here, my total resistance would be 15 ohms. So my total current in this circuit, again this circuit being 100 volts and 15 ohms, my total current in this circuit would be 6.67 amps. So we have 6.67 amps running through that 15 ohm resistor. That's a combination in things in series. So I have 6.67 amps running through the 5 and 6.67 amps running through the 10. I have less current there because removing a resistor in parallel increased the total resistance, which decreased the total current. All right, that is our review.